All right, let's talk about our last set of notes for this unit, and that is power and efficiency. All right, so maybe you're like me and you're singing, I got the power. All right, so that's what I always think about with this. So just have that playing in the background of your mind this entire time. It makes the whole thing that much better. All right, so we have been talking about work and about energy and all of that. So we're still talking about all that. So power is the rate at which work is done. All right, and whenever we have the rate of something, that means that we're timing something. So now we are timing work. Like, how long does it take the work to be done? All right, so we have our first formula for power, and that is power is equal to work over time. All right, so we have two different units for power, and that is the watt. All right, the SI unit, the one that we're going to be using is the watt. Now, don't get confused because watt is a capital W and then work is a capital W. But this capital W is a variable. This is a unit. All right, work, this W is a variable, this W is a unit. Please do not get that confused. All right, there is also another unit called horsepower. All right, everybody should have heard of horsepower. We see that on motors. All right, so we do not use horsepower in our calculations because it's not the SI unit. So we do have to, we do have to convert horsepower into watts. And we use this conversion right here. So 1 horsepower is about, and you'll see what I mean by about 750 watts in just a second. You do not have to memorize that. I will give that to you. All right, so why do we use horsepower? All right, so that was one of the earliest forms of the units of power. And the way they found the conversion, so our horsepower and watts, is they took a mass of 75 kilograms, a horse moved it 1 meter in 1 second. All right, so whenever we take that, whenever we look at it, all right, let's look at this box. All right, let's draw the free body diagram for this box. All right, so we know that gravity is pulling it down, and this is a tension force that is pulling the mass up. All right, so we can assume that it's going at a constant speed. So that means that these two are going to be balanced. All right, so if we're trying to find the power, we know that that is work over time. All right, so we've got our time of 1 second, but we don't have work. But we do know that work is equal to force times displacement. So we can put in force times displacement over time. We still have time. We now have a displacement. Our height is 1 meter, but we don't have force. All right, so we've got to do a little thinking. So we are trying to find this force right here. But we know that that force is equal to Fg, our weight. All right, so we know that Fg is equal to mg, so we can sub this in for the force because we know that they are balanced. All right, so we can break that down even further into mg times d over t. Now, we now have all of those. So whenever they plugged it in for this 750 watts up here, they just estimated, they rounded gravity to 10. So that would give us 75 times 10 times 1 over 1, which would give us 750 watts. This one is whenever you use actual 9.81. So just use whatever I give you on the test. Most of the time for your lab, we will be using the 750 watts because it's just an easier number to use. All right, so let's look at this next thing. All right, so say that we have a mountain. All right, so we've got twins. We're going to say we've got one twin is going up this side and then one twin is going up this side. All right, they're going to be identical, meaning they're identical in mass, identical in weight. All right, so this twin decides to be a rock climber. So this is the rock climbing twin. All right, and then that rock climber takes the hard route up the side of this mountain. All right, so it takes him a really, really, really long time to elevate just a few meters along that side. Now, we're going to say that this twin is a trail hiker. All right, so she is going to just go up the mountain easy as you please. All right, so it does not take her very long at all. All right, so she does it in a short amount of time. Now, what I want you to see here is that they are going the same distance. Both of them are going the same distance, and they both are identical in weight, which means they are exerting the same amount of force. All right, so remember that work is equal to force times displacement. So these twins are doing the same amount of work, but one is doing it in less time. The one who does it in less time has a greater power rating. All right, so say that your work for both of them was 2. All right, so say for the rock climbing twin, it took him 4 seconds. Say for the, or 4, yeah, we'll just say 4 seconds just for number wise. All right, and say for the hiker, she did it in 2 seconds. All right, so the rock climber had a power output of 0.5, while the trail hiker had a power output of 1. All right, so even though they did the same amount of work, the trail hiker did it in a shorter amount of time, so she had more power, that 1 watt. All right, so whenever we talk about power, we're talking about machines. All right, so so up here we were still talking about machines, but our bodies were the machine, or the twins' bodies were the machine in question. All right, so whenever we talk about a powerful machine, we think of those as strong and fast. So strong meaning a big force, fast being a high velocity. All right, so we have already broken down power into work over time, and we've already broken down work into force times displacement. All right, so we've seen this part before, this breakdown before, but we're going to look at it, we're going to deconstruct it a little bit different. All right, so the other time we deconstructed force into mass times acceleration due to gravity times displacement over time, but we're not going to do that. We're going to keep it like this. We're just going to rearrange it. So we're going to take force out and then multiply that by displacement over time. Well, we should know that displacement over time gives us velocity. So this brings us to our second equation for power, and that is force times velocity. Power is also equal to force times velocity. All right, so we still got that from power is equal to work over time. We just broke it down a little bit different. All right, so let's do our first example. So we have a 193 kilogram curtain that needs to be raised 7.5 meters at a constant speed in as close to 5 seconds as possible. All right, so we have 3 different motors. We have a 1 kilowatt motor, a 3.5 kilowatt motor, and a 5.5 kilowatt motor. All right, we want to know which motor is the best for the job. All right, so if we want to know which one of those motors is best for the job, then we need to know how much power it's actually going to take to lift this curtain 7.5 meters in 5 seconds. All right, so that's what we're going to do. So we know we have a mass of 193 kilograms. We know our distance is our height of 7.5 meters. And we know that our time is 5 seconds. Now, remember, we do need to take into account, we need to look at the free body diagram. All right, so this curtain, as it's being pulled up, is being, it has two forces being exerted on it. So it's got that tension force pulling it up, and it's got that gravitational force pulling it down. But it's going at a constant speed, so that tells us that these two forces are balanced with each other. All right, so we have everything that we need to solve for power. All right, so we know that power is equal to work over time. Once again, let's look at our givens. We have time, but we don't have work. So we know that work is equal to force times displacement over time. We still have time. We now have a distance, but we do not have force. All right, so we go back to our free body diagram. All right, technically we're looking for this tension force, and we don't have an equation to necessarily solve for tension, but what we do know is that it is equal and opposite to our gravitational force, which we do have an equation for. We know that Fg is equal to mg. All right, so we can sub in mg for our force times distance over time. So now we have mass, we know g, we have d, and we have t. So we can just plug it into our equation. So we have 193 times 9.81 times 7.5 all over 5 seconds. All right, so our total power rating for this is, what is it? Okay, 2,840 watts. It's 2,840 watts. All right, so if I were just asking for the power needed, this would be your question, or this would be your answer, excuse me. But that's not what I asked for. I told you that we had 3 different motors, and we wanted to know which motor is best for the job. But let's see the unit that each of our motors is found in. It's found in kilowatts. Well, we just have watts. So in order to really see the difference, we need to turn, that's 2,840 watts into kilowatts. And we know that for every 1 kilowatt, there are 1,000 watts. So we divide 2,840 by 1,000. We do get 2.84 kilowatts. All right, so it's going to take 2.84 kilowatts to raise this curtain. All right, so we look at our motors. Is the 1 kilowatt going to work? No, it does not have enough power. The 5.5 kilowatt, it does have enough power, but that's kind of overkill. So our best answer would be the 3.5 kilowatt motor. It has enough, obviously, but it has just a little bit more. So the 3.5 kilowatt motor would be the best choice. All right, let's look at this one. If an automobile engine delivers 50 horsepower of power, how much time will it take for the engine to do 6.40 times 10 to the 5th joules of work? All right, so let's write down our givens. We have been given power in horsepower. A big red flag should be being thrown up in your brain. All right, horsepower is a unit for power, but it's not the one that we use with our equations. So we do have to turn this into joules. Remember, not joules, watts. All right, so we do know that there are 750 watts in 1 horsepower. So we multiplied that by 750, and we do get 746. Let me just plug it into my handy dandy calculator. 50 times 750 does give us 37,500 watts. All right, we've been asked how much time, so we're looking for time. For the engine to do 6.40 times 10 to the 5th joules of work. All right, so we know power, we know work, we're looking for time. All right, so we've got power is equal to work over time. Solving for time. It's in the denominator. We do not like that. So we have to get it out of the denominator first and foremost. So we multiply both sides by it. All right, that gets it out of the denominator. So we have power times time is equal to work. Still trying to get time by itself. So we divide by power. All right, so time is equal to work divided by power. So we have our work, which is 6.40 times 10 to the 5th joules divided by 37,500 watts. We divide those, and that should give us about 17.2 seconds. 17.2 seconds. So it takes 17.2 seconds for this engine that has 50 horsepower to do 6.40 times 10 to the 5th joules of work. All right, the last thing that we're going to go over is efficiency. All right, so all efficiency is, we're still talking about machines. We want to know how efficient a machine is. All right, so we want to know how well it works. All right, so we've been talking about the conservation of energy and all that kind of stuff. So if we were to have a frictionless system, no friction, we know that energy is conserved in a frictionless system. So that means that no energy would be lost to the surroundings. All right, so that means that the amount of work that we put in is equal to the amount of work that we get out. And so our efficiency would be 100% efficient. All right, that would be great if that were real life. But in real life, we do have friction. All right, friction is everywhere. We have actual friction and we have air resistance, which is a type of friction. All right, so because we have friction, we are going to lose some of that energy, some of that work that has been put in, because it's going to give it off as thermal energy, heat energy, sound energy, all of that good stuff. So we will never in real life have a 100% efficient machine. All right, so remember that efficiency is going to be a percentage. All right, it's a ratio, so a percentage. And remember, all percentages are part over whole times 100. Part over whole times 100. Well, if we try to think about what would be the part, what would be the whole, our whole is going to be the amount of work that we put in. All right, the part is going to be the amount of work that we get out of it. All right, because our work out is always going to be less than our input work. All right, so that's what this says. All right, because of friction, our work output is always less than the amount of work input. All right, so that's going to give us this equation. Our efficiency is work out over work in times 100. All right, so our last example is asking us to prove the efficiency of a machine that has an input of 100 joules and an output of 40 joules. So remember, efficiency is equal to work. Oh, I don't know what that was. Interesting. It is work out over work in times 100. All right, so we have work out that was 40 joules over work in that was 100 joules times 100. Well, we know 40 divided by 100 is 0.4 or 0.40 times 100 is going to give us 40%. So this machine is only 40% efficient, which is atrocious. All right, we want as close to 100% as possible. All right, so that concludes our notes for today. Let me know if you have any questions.